Hello everyone. Today we will do some questions based on convergent sequences. Let us first recall the definition of convergent sequence. A sequence AN is said to be convergent to a real number L if for every epsilon greater than 0, however small, there exists a positive integer capital N depending over epsilon such that the distance with an minus L is less than epsilon for every n greater than capital N. Here capital L is called a limit of sequence AN, and we write it as limit AN where n tends to infinity is equals to capital L, or we can also write it as AN tends to L as n tends to infinity, or we can directly write it as AN tends to capital L. Let us make an understanding of this definition. Here the blue points are depicting my sequence points over this graph. When the n is 1, my a1 is here, and when n is 2, my a2 is here, and we can see that points are firstly decreasing and then increasing, or some they are just in a zigzag form, and after this point n they are going close to this number L. So here L is my limit of the sequence, and all the terms of the sequence after a particular point n are converging to the point L. So this is the graphical meaning of a convergent sequence. Now we need to make some notes here. There are some direct results available. The first one is, if a sequence is convergent, then it converges to a unique limit point. There is no case in a sequence where it is converging to 2 points. Always a convergent sequence will converge to a unique limit point. Secondly, every convergent sequence is bounded, but converse of this statement is not true. For example, if I take a sequence where an is equals to 1 by n, this is my convergent sequence and it directly converges to 0 as n tends to infinity. So this sequence is my bounded sequence. It is bounded between 0 and 1 for every n. But if I consider another sequence like an is equals to minus 1 to the power n, then this sequence is bounded as every term of my sequence is between minus 1 and 1. But this sequence is not convergent sequence as this will oscillate between minus 1 and 1 only. Third result, monotonically increasing sequence an converges if and only if it is bounded above. Further, the limit of an when it converges is the lowest upper bound of the given sequence. Similarly, if I have a monotonically decreasing sequence an and it converges if and only if it is bounded below. Further, the limit of an where it converges is greatest lower bound of the given sequence an. These are very important results to hold, and based on these results, let us practice some questions. In this question, we have to determine which of the following sequences converges or diverges. Give reason. For your answer. And find the limit of each convergent sequence. The first part is an is equals to 1 minus 1 by n. Now let us first check if this sequence is monotonic or not. Let an plus 1 minus an is equals to 1 minus 1 upon n plus 1 minus 1 minus 1 by n, and after subtracting this becomes 1 by n minus 1 upon n plus 1. Taking the LCM, it becomes n plus 1 minus n, and this is nothing but 1 upon n into n plus 1, and this term is always greater than 0. So therefore a n plus 1 minus a n is strictly greater than 0, implies the sequence a n is monotonically increasing sequence. So here we have to apply this third result, which says monotonically increasing sequence converges if and only if it is bounded. We have known that this first part 1 minus 1 by n is monotonically increasing. The further we have to show if it is bounded or not. So for boundedness, let a n is equals to 1 minus 1 by n. So we are subtracting some term from 1. So this term is always going to be less than 1, implies the sequence a n is bounded above by 1. Therefore the given sequence is convergent, and it converges to 1. Next part, where a n is equals to n minus 1 by n. Similarly, for monotonic sequence, let a n plus 1 minus a n is equals to n plus 1 minus 1 upon n plus 1 minus n minus 1 upon n. After simplifying, this becomes 1 plus 1 by n minus 1 upon n plus 1. So this is 1 plus 1 upon n into n plus 1. This term is always greater than 1. So it implies that a n plus 1 minus a n is also strictly greater than 0, implies the sequence a n is monotonically increasing. Now for boundedness, a n is equals to n minus 1 by n. So this sequence will directly goes to infinity as we will increase the value of n. So the given sequence is not bounded above, implies the sequence n is not convergent. Next question, where a n is equals to 2 to the power n minus 1 upon 2 to the power n. In this question, we will firstly simplify the given a n. This is 2 to the power n divided by 2 to the power n minus 1 upon 2 to the power n. We will separate the denominator to each term of the numerator. This become 1 minus 1 upon 2 to the power n. Now it is fine. Firstly, we will check if this is a monotonic sequence or not. So for monotonic sequence, let an plus 1 minus an is equals to 1 minus 1 upon 2 to the power n plus 1 minus 1 minus 1 upon 2 to the power n. This becomes 1 upon 2 to the power n minus 1 upon 2 to the power n plus 1, and when we take the LCM, this becomes 2 minus 1 and 1 upon 2 to the power n plus 1. This term is always greater than 0. Therefore, sequence an is monotonically increasing sequence. For boundedness, given an is equals to 1 minus 1 upon 2 to the power n plus 1, so we are subtracting something from 1 always. So this is always less than 1, implies the sequence an is bounded above. Therefore, the given sequence an is convergent and it converges to one. The next part, an is equals to minus 1 to the power n plus 1 and n plus 1 divided by n. This is a good question. Now we can simplify an first. When we are taking the value of n as odd, then it becomes 0, and when we will take the value of n as even, this will becomes 2 times n plus 1 by n. So we can write it as 0 when n is odd, and it is 2 times this when n is even. Okay, now we will consider a subsequence bn which is n plus 1 by n, and simplifying this becomes 1 plus 1 by n. Now we will check if bn is monotonic or not. Bn plus 1 minus bn is equals to 1 plus 1 by n plus 1 minus 1 plus 1 by n. This becomes 1 upon n plus 1 minus 1 by n is equals to n into n plus 1 n minus 1. So this is minus 1 upon n into n plus 1. This term is always less than 0. So the sequence bn is decreasing sequence. For boundedness, bn is equals to 1 plus 1 by n. So this term is always less than 2. Why? Because when we will take the value of n starting from 1, this will become b1 is equals to 1 plus 1, which is 2, and then it will become b2 is equals to 1 plus 1 by 2, which is 1.5, and if we take b3, this will becomes 1.1 by 1 plus 1 by 3. So this term is always decreasing sequence to 1 as n is large. So this sequence is bounded from below as well as bounded above. So we can say is bn is between 1 and 2. Since this is a monotonically decreasing sequence, so this sequence will converge to its greatest lower bound, not the upper bound. Hence, the given sequence Bn is convergent and it converges to 1. Therefore, the sequence An is 0 if n is odd, plus 2 times 1 plus 1 by n when it was even. When n is odd, an is converging to 0 only, but when n is even, this is converging into 2 times 1, because we have considered this term as bn, and it is converging to 1. So an is converging to 2 points, one is 0 and another is 2, but we have seen here that every convergent sequence, if it converges to a unique limit point. But in this case we are not getting a unique limit point, so this sequence is not convergent. An is equals to 2 plus 0.1 to the power n. Firstly, let us simplify the given term. It is 2 plus 1 upon 10 to the power n. For monotonic first. Let an plus 1 minus an is equals to 2 plus 1 upon 10 to the power n plus 1 minus 2 plus 1 upon 10 to the power n. 1 upon 10 to the power n plus 1 minus 1 upon 10 to the power n, and this becomes 10 to the power n plus 1 in the denominator, and 1 minus 10 is equals to minus 9 upon 10 to the power n plus 1, and this term is always negative, so this is less than 0. Therefore, an plus 1 minus an is less than 0 implies that this given sequence an is decreasing sequence. Now for boundedness, given an is equals to 2 plus 1 upon 10 to the power n, this is always greater than 2. Why? Because we are adding some little points into the term 2, so this term is always going to be greater than 2. Therefore, the given sequence an is bounded below by 2. Hence, the given sequence an is convergent and it converges to 2. The next, before going to the next question, let us make a note here where we have some standard limits. The first one is when limit n tends to infinity and an is of the form n to the power 1 by n, this is always equals to 1. Secondly, if limit n tends to infinity, we have some x to the power 1 by n, this always goes to 1, but there is a restriction that x value should be positive. Third one, limit n tends to infinity, x to the power n is equals to 0 only if mod of x is less than 1. Fourth one, limit n tends to infinity, x to the power n divided by n factorial is equals to 0 for any x. And the last one, an is equals to 1 plus x upon n to the power n. Then limit n tends to infinity, an is equals to e to the power x, and this result holds for any value of x. Let us do a question here. An is equals to 3n plus 1 upon 3n minus 1 whole to the power n. Before solving this question, we must simplify the value of an first. 3n plus 1 upon 3n minus 1 whole to the power n. What if we take 3n common from the numerator as well as the denominator? This becomes the power n. This got cancelled out and we are left with the numerator, which holds 1 plus 1 by 3n to the power n whole divided by 1 minus 1 upon 3n to the power n. And let us compare this result with the given question here. Here, in the numerator, we can consider the value of x is 1 by 3, and in the denominator, the value of x is minus 1 by 3. So, the numerator will converge to e to the power 1 by 3 and denominator will converge to e to the power minus 1 by 3. So, taking it to the numerator, 1 by 3 minus 1 by 3 is equals to 0, and an is equals to, here we should take limit n tends to infinity. This is the correct form to write here, so we should not be writing it as this. We should write as limit n tends to infinity, an is equals to e to the power 1 by 3 upon e to the power minus 1 by 3 is equals to e to the power 0 is equals to 1. So, the limit of the given sequence an will converge to 1. Next question. An is equals to 1 minus 1 upon n square whole to the power n. We can also simplify this term an as 1 minus 1 by n to the power n into 1 plus 1 by n to the power n. Taking limit is equals to limit n tends to infinity 1 minus 1 by n to the power n, and we can write it as separate limit for both terms. The first term will converge to e to the power minus 1 and the second term will converge to e to the power plus 1. So this becomes again e to the power 0, which is 1. So this sequence will converge to 1 again. The next one is an is equals to tan inverse n. We must know some results about this function tan inverse. We know here is tan inverse function is strictly increasing function. And it is bounded by minus pi by 2 and pi by 2. Since this function is given as monotonically increasing and bounded above by pi by 2, so clearly we can say that limit n tends to infinity tan inverse n will converge to pi by 2. The next question, an is equals to n minus Before going to the next question, we must add another note here. Suppose f of x is a function defined for all x greater than equals to n naught, and that sequence an is of real number such that an is equals to f of n for n greater than equals to n naught, then the function when x tends to infinity is equals to L implies that the sequence at n tends to infinity is also L. What this note say is that if we have a function which is defined for all the values of x except some points, and that sequence an is a real sequence such that an is equals to that function f of n, and it is also defined for all the values of n after n naught, then if we take the limit of f of x at x tends to infinity, it will be same as the limit n tends to infinity of an. Question based over this result is, when an is equals to natural log of n divided by n. Here we know that the function f of x is equals to ln of x upon x is defined for all x greater than equals to 1. Therefore, limit at x tends to infinity of ln x upon x will be equal to the limit n tends to infinity if limit exists. Now, to find the limit at x tends to infinity ln x upon x, this is an infinity by infinity form, so we apply L'Hopital rule. Then this limit becomes limit x tends to infinity 1 by x divided by 1. This is equals to 0. Therefore, limit of x tends to infinity f of x exists, and hence limit n tends to infinity an is also 0. We must note here is that by this note we have an understanding that if the given function is defined over some points, only then we can apply the limit directly. Otherwise, we cannot apply limit directly to the given sequence. Another question based over this same note is an is equals to 1 upon under root of n square minus 1 minus n square plus n. Have to simplify this expression an before solving. Denominator term contains the square root, so we will firstly rationalize these terms. We will rationalize it by n square minus 1 plus under root of n square plus n. The numerator will become n square minus 1 plus n square plus n whole divided by n square minus 1 minus of n square plus n. After simplifying, this expression will become minus of 1 plus n. Therefore, an is equals to under root of n square minus 1 plus n square plus n whole divided by minus of 1 plus n. Now, clearly this function f of x is equals to under root of x square minus 1 plus x square plus x whole divided by minus of 1 plus x is defined for all x greater than equals to 1. Therefore, the limit x tends to infinity f of x will be equals to limit n tends to infinity an if exist. So let us find out the limit of x tends to infinity f of x. This is equals to, if I take x common, then the expression will become 1 minus 1 by x square, and this will become x into under root of 1 plus 1 by x whole divided by, taking the x common here from 2, this becomes 1 plus 1 by x. This is equals to under root of 1 minus 1 by x square plus under root of 1 plus 1 by x whole divided by minus of 1 plus 1 by x. So we have taken the limit also. Here the limit also. So this becomes under root of 1 minus 0 plus under root of 1 plus 0 whole divided by minus of 1 plus 0. After simplifying, this becomes 1 plus 1 upon minus 1. This is minus 2. So the limit of x tends to infinity f of x is equals to minus 2, which exists. Therefore limit n tends to infinity an is equals to minus 2. Let us practice some very different question here. The questions says find the limit of the sequence an is equals to n minus under root of n square minus n if it converges. The given sequence is an is equals to n minus under root of n square minus n. After simplifying, we can say it as n minus n times under root of 1 minus 1 by n. There is nothing wrong in it. Now, we know that we can use the binomial expression for this term only. The binomial expression one plus x to the power p is equals to 1 plus p times x plus p into p minus 1 upon 2 factorial into x square plus so on to. We will restrict this binomial expression to the two terms only, that is till p of x only. Now let us expand the given term 1 minus 1 by n to the power half is equals to 1 minus 1 upon 2n minus 1 upon 8 into n square plus so on to. Since we will expand this term to the two terms only, therefore an become approximately equals to n minus n into 1 minus 1 by 2n and so on to. Approximately equals to n minus n into 1 minus 2n. This term is equals to n minus n plus 1 by 2. This is equals to half. Therefore an is approximately equals to the term half implies the limit n tends to infinity is half as it becomes the constant sequence is convergent. I hope you have made an understanding about these questions, that how we can say if a sequence is convergent or not. Happy learning!